Thank you for a kind introduction. My name is Kevin Koosup, a research scientist working in SINTEF Ocean in Norway. And SINTEF Ocean is an independent research institute working in the area of maritime and offshore energy industry. And in these days, we're working toward decarbonization and also digitalization technology, which fits perfectly to this theme of this conference. It is a great honor to be invited to this prestigious event. And today I'll talk about how open simulation platform is used in the industry in Norway. First, I'll begin with the motivation for open simulation platform. In short, OSP, or need for system simulation in the development of complex system. Then I will continue to explain what OSP is and the output of the project. Next, I will introduce a new development project based on OSP, Integrated Simulation Sandbox, which intends to widen its application in the industry. From yesterday's presentation and discussion, we already have learned that shipping industry is facing a great challenge to mitigate climate change. It looks like that we have a set of solutions, but the pathway is still unclear and uncertainty is higher than ever. If we combine all the known technologies and solutions that we know as of today, we may be able to reach the goal quite soon. But the question is how to do it in an economically viable way in the global scale. The real challenge lies in the complexity of the problem. There are a great deal of uncertainties related to changes in rules and regulations, fuel price, market situations, and policy changes. Which combination of solutions will be most affordable and suitable for the given operation profile of the vessel, considering its mode of operation, route, speed, and weather conditions, which will also change in the future. Then we need to think about 20 years ahead for the vessel's lifetime. And this is a formidable task to come up with an optimal solution. Let me illustrate a simple example. How many options do we have to consider to come up with an optimal design? Let's start with a hull design. Maybe we have 10 variants that we can look into. And we have more fuel options and propulsion options. Maybe 10 variants we can look into. Then that makes 100 cases to examine. And in these days, control strategy is very important to make the ship operation efficient. And there are variant ways of doing this. And then we can come up with 500 cases to examine and test and verify if our solution is good enough. And as I said, the vessel is operating in very different conditions, weathers, routes, and different speed policies. So that makes quite complicated operation profile that we can look into. So then it's just increasing in numbers. And at the end, we can reach a number of cases that is impossible to analyze with our current technology. One way to tackle this challenge is to rule out a number of options and narrow down our design choices in early stage by introducing system simulation. From the day one, we have a great ambition to create a perfect system, efficient, reliable, and effective system. And during the development, we are iterating with our ideas, design, implementation, and integration. And we want to test what has been created to make sure our system follows the requirements and expectation. And test should be done in the whole system perspective, not to miss out our important characters and the system behaviors. And introducing system simulation will help to a designer or developers to test their systems on the way to reach their system in operation. But it is difficult to set up the simulation due to lack of experience, expertise, and non-collaborative working environment, and knowledge is lost during the path, and also the process is very segmented. So, what is OSP, and what does OSP try to solve in this context? The Open Simulation Platform, OSP, aims to provide the means to create a system simulation model in a collaborative way by easily exchanging the models, reusing them, while protecting the intellectual properties rights. It is open source industry initiative for co-simulation for marine equipment, systems, and entire ship. It follows and provides common standards for collaboration across stakeholders. And we launched OSP JIP joint industry project with 27 international partners in 2018. And we completed the project last year. And we came up with the main 4 outputs. First output is co-simulation software that is provided as an open source software. The next one is OSP interface specification, which defines a standard for interfaces between models. The third output is OSP reference models. It's a kind of model library which has different types of models, different types of system configuration, which shows the example of how to set up the system in OSP environment, and also provides some the models that you can start your system modeling. And finally, there were use cases that demonstrated the feasibility of the methodology in different life cycle of a ship, design, commissioning, and operation. But practically, what do you need to run a system simulation when you are thinking of OSP software? First, you should have models. And models are packed as files called functional mockup units, FMUs. And you can use the OSP software, which is open source and freely available. And then you need to configure your system models. And your system model is defined in OSP system structure file, which is text file, which contains the information of what components are included and how the components are connected in different connections. And these 3 are must-haves to run a simulation. And in addition, you can also describe more advanced connections following the OSP interface standard in this OSP model description file. And also you can add more advanced simulations features like scenarios and what parameters will be logged at the end of the simulation. So except this OSP software, which is a binary file, and also FMUs are binary files. Except those, all the configuration files are XML files or JSON files, which is structured text, which can be easily edited. And this provides a great advantage for developing a new software tools to configure simulation, since manipulation of these texts are very easy, especially when these texts follow this well-established standard. So when the joint industry project was completed last year, our goal is then we continue by providing this open source software specifications and example configurations from the JIP, which will form the basis of an active open source community around the OSP project. And in parallel, DNV has developed a platform service called Trust Center. And it has been launched this year that can manage secure sharing of models, assurance of simulation models, and an infrastructure to perform efficient system simulation on neutral ground. And then in the industry, or together with academia and a research institute, we continue to develop this open simulation platform into more usable forms in their process. And that's where we are talking about what we are talking about today further on. Then what is Integrated Simulation Sandbox? It's another name, and then I call it ISB. Even though OSP has established a very good foundation for a collaborative way to build a system model across the industry, the software itself is still deemed to be difficult to use by the industry. Creating a system simulation model by establishing all these connections between the components became easier with the OSP interface specification, but it is still beyond the comfort zone of the ordinary engineers and developers. So together with our industry partner, Hav Group in Norway, and we are carrying out this free-cost project where we try to build a large-scale hydrogen-powered ferry in Norway. In this project, we're trying to develop a new simulation platform that can be easily used in the daily tasks of engineers and developers. Such a software development, software platform, should be where multiple users can create and manage system at the same time for co-simulation. And it should provide intuitive graphical interface and integrates their workflow. And we call it Integrated Simulation Sandbox, in short, ISB. So what can ISB be used for? It's the same as OSP actually. It can be used for system performance analysis, or it can be used for testing control system using the X-in-the-loop testing methodology, hardware-in-the-loop testing, software-in-the-loop testing, or model-in-the-loop testing. Or you can use it for virtual commissioning or operation planning. So it's very similar concept as digital twin presented by Mr. Choi today. But who can use the ISB? That is what differentiates the ISB from OSP or other simulation software. Traditionally, a complex system simulation has been an area of simulation experts. For ISB, our target users are average engineers for standardized simulation, while it can still provide generic functionalities for special purpose simulation for simulation experts. In terms of domain, we target our users as ship designers, system integrators, and domain experts. In short, whoever is interested in the system interaction and holistic performance of the system should be able to use it and benefit from the simulation. And to build such a software that provides the key features mentioned, we are developing ISB as a web application where users can log in from wherever they can access, and they can have access to the models and interact with them. A user can upload models to the server and share with others. A user can also configure the system using this intuitive user interface and set up a simulation. All the works done in the platform is stored in the database and retrieved by the users or others from if they have a right access right. And the software has main three features. The first is FMU management, where people can upload models to the server. And they can also create some special FMUs that will do particular functions and using the FMU templates. The second feature is system configuration, where a user can add components and connect the models, or they can use a configurator to come up with system model with a certain set of parameters put in. And finally, it can also support simulation configuration, where users sets the test scenario and login configurations. And the software is developed through the actual use cases to include the users in the development loop and receive their feedback to make the tool be usable and useful for users. And the purpose here is to find the right level of complexity that the designers and engineers can cope with. We found that the system configuration, as it is usually a difficult part for our users. So this is the example of a system configuration having the hull propulsors and the power system, switchboard, gensets, and batteries. It's a full-blown, like an entire ship simulation setup. And for average users, connecting and identifying all the interfaces and connecting them together is a very hard burden. So our users pointed out that creating such a model is beyond their comfort zone and not really value creating for their daily tasks. So we decided to develop a configurator for standardized system models such as vessel system simulation or power system simulation. And this is possible as we will work with a well-defined set of FMUs and well-defined connections between the components. So a system model created in this way can be further connected with also additional components by using these generic configurators. So for example, this vessel system configurator, the system model can be first configured and created in the hydrodynamic workbench that the hydrodynamic knows very well how to use it. And the workbench can generate files that can be imported to this ISB platform. And these files will be imported and ISB will create a system automatically. And same with the power system model. A user can define the system by creating a single line diagram, which is shown on the left, lower left, which is a well-known system architecture diagram for a power system. And then the system or ISB can translate this system architecture into a system model. And user can extend the model by adding more components such as vessel, hull, and propulsors, and other subsystems or controllers. That's under development at the moment. So using these configurators, our users are trying to use the simulation for their actual need for the development. This use case here intends to connect the autopilot system from the Norwegian electric system to the vessel system models created in the ISB. To communicate with the actual system, actual control system from the simulation model, we found that we need more models like sensors and communication modules. And these additional models and modules are under development at the moment. And by the end of the day, users will be able to create a perfect system model for testing their controllers and auto-tuning the parameters by a set of clicks and well-defined parameters that they know very well. And another use case we are defining at the moment is the maneuvering simulation of a vessel with a power system in the loop. The purpose of this use case is to observe the system response during the maneuvering in the very demanding weather conditions, where the power system sets some kind of limits on the thrusters. So then the vessel will behave differently than when the power system is ignored in modeling. So power system configurator will be developed in parallel in this use case. So now we are reaching the conclusion of the presentation. So we have seen that a system simulation will ensure the the quality and reliability while developing this complex system. And OSP, we have seen that it provides a foundation for a collaborative way of creating a system model of marine equipment and whole vessel. And ISP aims to deliver this benefit of OSP to the hands of ordinary users, ordinary engineers and developers. And I believe that the real innovation starts when the tool is being used by these ordinary actual projects and development. I think engineers always find a way and usage that we haven't imagined when we design this platform or when we develop the software. And we'll try to bring the technology available to the daily routines of these daily engineers and make innovations together. Thank you for your attention. Thank you.